Okay, good evening, ladies and gentlemen, boys and girls. Welcome to Science Center and also welcome to the Science Cafe organized by Science Center. Yeah, so today we have a topic about black holes and a cup of tea. I wonder if, a lot of times, many times when we think about science fictions, you link to something, wormholes or time travel. So quantum mechanics and black holes, these are things like often features in the science fictions today. Is like inspired us to have more imaginations. So general relativity was published by Einstein in 1915. And it predicts the existence of black holes. In our galaxy, there's a supermassive black hole. It's called Sagittarius A star. So this is discovered, and a lot of effort has been put in to discover new black holes and also to study the black holes. So in the black holes, it changes because of the strong gravitational force, it changes the space, the mass, the momentum, the energy of the matters. And this is really something fascinating because when the energy goes or light goes beyond the event horizon in the black holes, it seems like it never returns. It will go, without anything. So whether this will emit radiations or you can observe it, so this is the current challenge. And today we have Dr. Lim Yen Keng from National University of Singapore Physics Department to talk about black holes. So Dr. Lim Yen Keng is an instructor currently, and he graduated as a PhD in physics in 2015. Today he will talk about about one of the maybe most interesting thing about Hawking radiations. So how Stephen Hawking contributed to the black hole study. So we welcome Dr. Lim for this interesting talk.
Okay, thanks. Okay, hi everyone. Good evening. So I'm here to talk to you guys about this, right? So I understand the event. The name of this event is Science in the Cafe, and this is a black hole and a cup of tea. And I assure you, it is a coincidence because there is a cup of tea in this story, right? In this story of the development and the history of black holes. And Stephen Hawking himself was part of this development. Okay, so I guess partly the reason why we're here is to celebrate the life and contributions of Professor Stephen Hawking. His research area is on black holes, Hawking radiation, quantum gravity, and also black hole thermodynamics. So I'm gonna sort of take you through all this, right? And it's going to be a long story because the history of general relativity is quite a long history. So I say it's a long story, it's not complicated story. So yeah, a lot of people ask, they're sort of intimidated by physics, right? This guy's complicated. Doesn't have to be, right? So I'm gonna say it is a long story, it's not complicated. Okay, so Game of Thrones is complicated. Taiwanese drama is long, 500 episodes. So it's one and the other. So I'm gonna start with this long story. And because we want to understand Hawking's contribution, right, which is ultimately the main thing I want to talk about is Hawking radiation. In order to understand Hawking radiation, we need to understand black holes. And to understand black holes, we need to understand general relativity. And general relativity is a theory of gravity. So that is where we shall start, right? So I'm going to talk about general relativity. So don't worry about equations here. I'm just putting it here for decoration. And Apple is historically an important part in the development of gravity, right? I guess some of you guys know the apple fell next to Isaac Newton and it inspired him to develop his theory of gravity. So I'm going to start with Einstein. but not from the early days of Einstein. So I'm going to start at sort of like the end, halfway through Einstein's career when he's already establishing his new theory of gravity at the time. So yeah, general relativity. And by that time, he has already developed his theory of special relativity. So special relativity is a theory that sort of replaced Newtonian mechanics. So I guess students in school, they learn about objects moving, how fast they move, the forces. That is Newton's theory. But it is not applicable for objects moving really fast. So Einstein fixed that, right? So that is, he already developed this, and now he's developing his theory of gravitation. Okay, so in this picture, I'm showing you two people, right? This is Albert Einstein and this is Arthur Eddington. And I'm basically going to recap the story that you can actually watch in a movie, which is here, right? So David Tennant and Andy Serkis, they played Einstein and Eddington in this movie. It's quite interesting if you can find it. It's quite a good movie. So yeah, you guys know him as Doctor Who and Gollum from Lord of the Rings. So yeah, so what is this theory of gravitation? Well, what is Einstein's radical new idea at the time? His radical new idea is that the force of gravity is actually not really a force. It is a curvature of space and time. Okay, so that is a bit weird, right? So we need to explain that a little bit. So what is gravity about? So gravity is about like things that are falling to the earth, right? So earth has a gravitational pull. It pulls everything together. Okay, so that much we know, right? So that much we know since the days of Newton for 400 years. So Einstein's radical new idea is that this force is not actually a force. It's sort of like curvature of space-time, right? And gravity is caused by planets with big masses that is so massive that it can, it can cause dents and it can curve the fabric of space and time around it. Okay, so yeah, if that sounds confusing, let me explain with this very common analogy, right? So imagine, right, space and time is a fabric that can be distorted, right? So we know what is space, up, down, left, right. Time is time, right? And that can be distorted by gravity. How? So imagine the fabric of space and time is like your bed sheet you stretch out, right? So a blanket or something, right? You stretch out. So if there's nothing on it, then everything is flat, right? So when everything is flat, if you roll a marble on it, it will just go on a straight line. Okay, so everything is fine. So what happens when you put a basketball in the center of your blanket? It's going to cause a dent in the middle of the blanket, right? So it's going to cause a dent. Then what happens if you roll a marble for that case? So if you put a basketball on the dented bed sheet, and then you flick a marble, the marble is just going to roll around the basketball. Right? So that is what gravity turns out to be. Okay? So kind of like this picture. Okay? So yeah, space and time is something like a fabric, and something large like a planet Earth can cause a dent around it. Okay? So then what we see as gravity is, this explains the behavior of why the moon orbits around the Earth, or why things fall towards the Earth. Why Earth has a gravitational attraction? Because imagine you're doing this experiment, right? You have this bed sheet, put a basketball on it, it's dented, okay? And imagine you turn off the light so you don't see the bed sheet, okay? And you paint your basketball with something that is glowing in the dark, and your marble that's glowing in the dark. So you only see the basketball and the marble. You turn off the lights, you don't see the bed sheet, right? So if you don't see the bed sheet, right, what do you see is, well, the marble going around a glowing basketball at the center. It's as if the basketball is attracting the marble, right? So that is what Einstein's new idea is, right? It's not actually a direct force, it's just a curvature of space and time, okay? So you might say, right, okay, fine, what's the big deal, right? Just a different interpretation, okay? And just a different way of viewing things. So why is it different from Newton's law? The difference is, this interpretation can have a prediction that is not accounted for by Newton's theory of gravity. So Newton's theory did not even consider what happens to light. And I'm going to be talking a lot about light today because a lot of great revolutions in physics sort of began when physicists asked questions about light. Okay, so Newton didn't even consider light. Gravity doesn't affect light. But if Einstein theory is correct, that space and time is curved by a planet, then light also travels along space and time. So when you shine light along this curved path, then the path of light will also be affected by gravity. Okay, so that is, so that means something like this should happen, right? So so something like that should happen, and to test whether Einstein is correct, well, we need to see whether this thing can happen or not, right? So if we want to look at a distant star, okay, if Newton's theory is correct, it doesn't affect light, so light will just travel in a straight line, then we will see star at this position here. Okay? But if Einstein is correct, then the fabric of space and time is dented by a large mass like the sun. Then the position of the star is a bit off-center, a bit in this direction. Okay? So that means, well, there's only one way to find out who's correct, right? Newton or Einstein. Just look at the stars around the sun, and there you see a problem, right? So how do you see a star around the sun? You see the sun there, and you can't see anything else, right? It's daytime. You can't see stars. So that is where Arthur Eddington comes in, right? So a few years after Einstein published his theory, there was an eclipse, there was a solar eclipse that's about to happen. Okay, do you know what is a solar eclipse? Solar eclipse is when the moon blocks out the sun, right? So during daytime, the moon passes in front of the sun, it blocks out the sunlight, so the sky becomes dark and we can see stars. And during the solar eclipse, Arthur Eddington he measured the position of a star, and it turns out that it's true. The position of a star has been shifted to this direction. And that is when Einstein and Arthur Eddington become famous, right? So Einstein was proven right? So it turns out that gravity actually does affect the path of light. Okay? So an object, and the reason why Newton and everyone didn't notice until this is because you require something really, really heavy in order to curve the path of light, right? So something as light as me, right, is unable to curve the laser light, right? Something as heavy as Earth is also still not enough, and you need something as large as the sun to only curve by just that little bit that is just barely enough to be measured by Eddington. Okay, so you need a really strong mass to curve this. That's why it's not observed until now. Until now, when technology gets improved, then we can observe more and more things. Okay? So now I will go through a little bit more detail. So I'm just redrawing this diagram again. When you have a very strong planet or strong star, planet is not enough, right? A really strong star, right? Nearby. So when the light shines, normally light should travel on a straight line, but because it curves the space and time, right, the direction of the light will be bent, and this is something that physicists can measure. Okay, so that is what happens when you have a strong mass, and this is sort of a precursor to what I'm about to mention. Okay, if you are somewhat familiar with black holes, you sort of see where this is going, right? If I have the same mass, but if I squeeze it to a smaller size, okay, the path of light is still the same. Okay, it's still the same. You can't tell unless you shine a light a little bit closer, right? A little bit closer, so that when it's closer to your gravitational source, then the bending will be a bit more stronger than this path that is shown a little bit further away. Okay, but that's the problem, right? You need a really strong mass in order to bend the path of light. Okay, otherwise, yeah, as we know, like this laser pointer, light travels on a straight line. Okay, but if you are able to find a mass that is strong enough, okay, that's strong enough, it will bend more. Okay, so even stronger, it will bend even more until maybe it is possible that if the mass of the object is strong enough that it can bend in this way, right? From this line, right? Your light shines coming out of this line, bends around and intersects the line again. Do you know what that means? That means the person standing here, right, is able to see something that is directly behind this thing. Okay, such a strong bending. Okay, so it sounds a bit drastic, right? Right. Normally, if I stand in front of something, you can't see anything behind me. So that means I'm too light. Okay, so I'm not heavy enough. So that's good. You can't see anything behind me. But if you find a mass that is strong enough, okay, the light from behind me is able to bend around it and go into your eye, right? So then you might say, okay, that sounds a bit extreme, right? Because such a thing can happen or not. Okay, yeah, the younger people might say pigs already didn't happen. Here's a pig picture. Okay, so this is what we call the gravitational lens. Gravitational lens is, you see this round thing, right? Yeah, you see this round thing, and then this thing at the center. So this is the mass I'm talking about in all the diagrams I'm drawing. So something with a really strong mass is able to bend. And why does it have this shape? So this is a distorted image of something that is supposed to be directly behind this galaxy. Okay, so this thing, right, is supposed to be directly behind this, but light is traveled around the galaxy and into the camera, right? And why is it round? Because the light path can travel, as you can see from this picture, it's possible to travel this way, goes into the camera. Another light can travel this way, goes into the camera, and some other light will travel on one side, and then one goes the other side. Okay, so all around, right, after all directions, you can see this circular shape. Okay, so it's a distorted image of a galaxy that is behind it, and that. So because it's a distorted image, right, this is like what lenses do, you know. So if you have specs, right, if you move your specs around, you see the image being distorted. So it's like a lens. And this is what we call a gravitational lens. Okay, so yeah, so light, actually, if you can find something with enough mass, it can bend all the way around and to have this effect. Okay, so yeah, basically that is what we call for gravitational lensing. And as I said, right, if you're sort of already familiar with black holes, you see where I'm going with this. I'm sort of easing you into the idea that the gravitational effects can be very strong on light. Okay, so look, gravity can attract light. And again, this is just decoration, right? Forget about all these equations. I'm going to talk about black holes now. Okay. So what are black holes? Yeah, so black holes is something that we have been working on since the days of Einstein, right? It is one of the first, well, I'm going to talk about that later, but black holes are something that is very massive and very dense, so the gravitational effect is really, really strong. And it is predicted by Einstein's theory. Okay, so Einstein have a theory, and once you have a theory, you have all kinds of implications and consequences, right? And we leave it to the physicists to work out what are the consequences. And black holes are one of them. So what are black holes? So black holes are supposed to be something that is so dense that gravity is too strong. And the best way to introduce the concept of black holes to you guys is to think about the concept of escape velocity, right? Because we are on a planet, right, Earth. We are on the surface of the Earth. So we feel the Earth's gravity, okay? So now I ask you this question, okay? We are attracted and we're stuck on Earth. So what would it take for you to escape the gravitational pull of the Earth? Okay? So according to physics, in order to escape the gravitational attraction of the Earth, you need to launch yourself with a sufficiently high speed. So that is what we call the escape velocity, and that's how rockets work. But actually, for most rockets, right, the satellites that they launch do not completely escape from the Earth. But the idea is that, okay, so in order to escape from the planet, you need to have enough velocity. So how fast do you need to escape the surface of the Earth? The answer is 11.2 kilometers per second. Okay, so yeah. That is how fast you need to launch yourself from the surface of the Earth on sea level, right? 11.2 kilometers per second. That is really fast, right? So our Earth's gravity is pretty strong, actually, even for such a small planet. So 11.2 kilometers per second. Right? If you drive car, right, it's like 60 kilometers per hour. This one is per second. So you need to launch yourself to completely escape from the Earth. And that is for the Earth, okay? And why do we have this number? Well, physicists do the calculation. Is because it depends on how massive the Earth is and what is the size of the Earth. So imagine if I squeeze Earth into a smaller size. Okay, if I squeeze Earth into a smaller size, right, it turns out that my escape velocity becomes higher. Okay, so that makes sense, right? Because why? Well, Earth is smaller, but all the mass has been squeezed into a smaller size. Everything is more compact. When everything is more compact, gravity is stronger. So when gravity is stronger, the escape velocity becomes higher. Okay, so that is what happens when you squeeze something into a smaller size. So imagine now, right? Let's continue squeezing. Right? Keep on squeezing and squeezing and squeezing. And we can actually know, right? For whatever size you squeeze in, the escape velocity becomes higher and higher. And we can imagine if you keep on squeezing all the way until a small size, the escape velocity becomes higher and higher until eventually the speed is so high it is the same as the speed of light. Okay, so if you can squeeze Earth into such a small size, then you need to launch yourself at the speed of light to escape. Okay. So that means even smaller than that, you need to travel faster than light to escape from the surface of that planet. Okay. So you see the problem with that now, right? What can travel faster than the speed of light? Nothing. Okay. So that is also Einstein's theory. Einstein's theory is that the speed of light is actually the fastest speed in the universe. Because to go any faster, you need infinite energy. Okay? So nothing can travel faster than light. And if your escape velocity is faster than the speed of light, that means nothing can escape. Okay? Not even light. So that is what the black hole is. Okay? So black hole is an object, right, that is so massive and so dense that the gravity is so strong that light cannot escape. Okay? So light cannot escape, and that is because light cannot escape, we can't see it. When we can't see it, to our eyes is blackness. That's why we call it a black hole. Right? And why a hole? Because hole is something that when you fall inside, you cannot come out again. Okay? So that's where the term comes from, black hole. Okay? So that is So that is black hole. And now a bit of like history. Okay? So this is Karl Schwarzschild and his mustache. So he's the first person to solve Einstein's equation. Just like 3 months after Einstein published the equations. So that's really fast. So then that happened in 1916. Okay, so he solved the first solution that describes a black hole. So black hole solution is one of the first results of Einstein's theory of gravity. Okay, 1916, just like 3 months after Einstein published his theory. And unfortunately, right, 1916 is also the time during World War I. And Schwarzschild sadly passed away soon after he published the paper. So that is his one contribution before he died during the war. So he's involved in the military, and he died in the front lines very soon after. Okay, so that is the first solution for the black hole. But it turns out, right, if you look further back into history, people has actually thought about the concept of black hole before through the idea of escape velocity. So they ask the question, okay, what is so dense that the escape velocity is the speed of light? So Michel and Laplace thought of that in the year 1746. But of course, during that time, there is no theory of relativity yet. So it's just like some crazy idea they had at the time. So Einstein's theory developed, and after Eddington proves it right, and with this solution sort of solidifies the concept of black holes. Okay? So now, every undergraduate in physics would know it is very difficult to solve Einstein's equation. Okay? So he somehow solved it very quickly. And then, then we have to wait 2 more years. So Reissner has 1916 some preliminary calculation, and Nordstrom completed it. This is a next solution called the Reissner-Nordstrom black hole. So it is a black hole with electric charge. And at that time, right, actually, how did they know that black hole can really exist in space was not fully established until 1939 with Oppenheimer and Schneider, where they sort of considered how a black hole can actually exist in space, right? So at that time, 1916 onwards, it's just some theoretical crazy idea, right? Something squeezed small enough that light cannot escape, but you need some alien advanced technology to squeeze it into this size. But then Oppenheimer and Schneider was studying the evolution of stars, and it turns out that stars, when they explode, they can turn into a black hole. Okay, so yeah, and then another one is the next solution came in '63. That is the Kerr black hole. So this is Roy Kerr when he came to Singapore a few years ago. He was speaking in NUS, and the next generalization is the Kerr-Newman black hole. So yeah, Newman contributed to a new solution to this. Okay. So anyway, these are just a few names. I won't go into much detail. Just giving off names that very few people heard about, so you can Google and learn more about it. Right. So black holes can have many different types. See, Schwarzschild solution is just the simplest one, spherical and neutral. The Rice nostrum have electric charge. Kerr black hole is a black hole that is rotating. Okay? Rotating black hole is another interesting story. Remember, right? Gravity is curvature of space and time. Right? It's denting the space and time. Okay? Now, if the star that collapsed and formed the black hole was rotating, right? So rotation also causes the effect of space and time. Okay? So it will sort of like turn around space and time a little bit. And that is the interesting effect known as the lens steering effect, and it is caused by the Kerr black hole. Okay? And the more general solution is the Kerr-Newman black hole. It is rotating and it has charge. Okay? Other black holes, I won't go into more detail, but black holes can also accelerate, and black holes can exist in a magnetic field. This is relevant for the center of the galaxy. Okay? But the interesting thing is for black holes, right? Even though solving Einstein equation is difficult, but the solution itself and the parameters is actually very simple. So we have the no-hair theorem. So what does that mean? So let me explain a little bit, and why is all these fun slides are here, right? So now the no-hair theorem. Let me state the theorem first, and then I'll explain why Patrick Stewart is there. So no-hair theorem is the idea that black holes can only be described by the mass and the angular momentum. If there's electric charge, there's charge. Only 3 numbers, right? If you know these 3 numbers, you know everything you need to know about the black hole already. That is a bit strange, because normally to know something you need more numbers, right? Compared to, let's say, Earth. Okay? So Earth has the mass, it has the rotation, we know it rotates once every 24 hours, but it has so many features that can distinguish it from other planets. Right? Because Earth, compare 2 planets, Earth and Venus. They are the same size, roughly the same mass, but they are so different planets. 2 very different planets, right? We can live and breathe on Earth, but when the minute we step into Venus, we suffocate to death. Right? So that is true for most systems, but for black holes, it's actually, no, it's not like that, because of the event horizon, everything just goes inside, so you just need to know the mass and the angular momentum. Okay, that's why we call it a no-hair theorem, because when people are bald and no hair, right, you can't really tell the faces apart. So that is why, Patrick Stewart in every movie looks like Patrick Stewart because he has no hair. Yeah, sorry Patrick. Yeah, I like you in X-Men. But compare, right? If you have hair, this one is the same person in the same TV show, but she's playing 5 different characters. Right? That's because you have hair, different parameters and acting skills, and so it's able to play all these different characters, and we even forget that it is the same actress playing it. So that is the idea behind the no-hair theorem. Okay, so yeah, I'm gonna skip this because I'm keeping an eye on the time. So basically, when a star dies, everything collapses, you form a black hole. So that's all we need for the rest of the story. Okay, and what about black holes that exist in space? So usually, right, black holes in space, they do not exist alone. Okay? Usually they are surrounded by clouds of dust and gas, swirling around it, falling into the black hole, falling into the black hole, and then it cannot escape. But outside, there's all the dust and gas all coming inside, collapsing into the black hole. Okay, so that is not swirling cloud of dust and gas, looks like a shape of a disk, and we call it an accretion disk. Okay. And so because of this, right, we can sort of estimate what would a real black hole look like in space. Okay? And remember, I was talking about light. Strong gravity can bend light, right? So the gravitational lens in the picture that I show you is the light source that is passing here, being bent by gravity and comes back to the observer on the line. But black hole is even stronger than that. If you shine a light even nearer, it will curve the path of the light and it will curve even more. And it can be even more extreme than that, right? So if you shine straight into the black hole, the light will just be pulled completely into the black hole. So not even light can escape. Okay? It's just fallen into the hole. And the interesting thing is the photon sphere. Okay, if you shine far away, it flies away. If you shine the light too near, it falls. So there is the right point of balance. If you shine at the correct angle, it is pulled by the Earth and being attracted into an orbit, and light is just orbiting forever outside the black hole. That is also an interesting feature of the black hole, which we call the photon sphere. Okay? So, let me show you a quick animation of how a black hole will appear if you look at it against the background of the stars. Watch out for a black hole coming in from the left. So this is the black hole coming in. It's bending the pictures of light around it. Can you see? Right? Because the path of the light is being bent around. Okay? So that's how the black hole would look like. Okay. So, have you guys heard of the movie Interstellar? Have you seen the movie? So Interstellar, that is the movie where you see a picture of a black hole, right? And people say it's realistic. And the news media say, oh, it is the first exact simulation of image of a black hole. Well, that is not actually true because he did it 35 years earlier. Okay, and he simulated the first known image of a black hole in the accretion disk. So notice that this is not a real picture. It's a result of a computer simulation. And the reason why it looks like a real picture is actually quite interesting because he did this in 1979, you know. So back in 1979, right, we don't have all this advanced computer yet. He was using the punch card computer and it's really slow. And back in the 70s, we don't have visualization, you know, LCD monitor and things like that, right? So everything is just data and numbers. So the punch card result that he calculated, right, all this raw data, he sort of draw by hand on a negative film, okay, point by point. So he draw by hand on a negative film, and that's why it looks like a real picture because he actually draw on the negative. And so it took a huge amount of effort to meticulously, you know, point by point, pixel by pixel, pixel is the name that we call today, but to draw this image. So that is I would say it is a phenomenal achievement, right? And we should credit him along with, you know, Christopher Nolan and Interstellar. But of course, Interstellar in 2013, technology is a bit more advanced. We have more advanced computers, so they are able to simulate a slightly more realistic picture, right? So so notice that one of the people here is Kip Thorne, one of the consultants of the movie, and he is the winner of last year's Nobel Prize, 2017. Okay, so he is also an expert on black holes, and he won the Nobel Prize for gravitational waves. Okay, so now it's tea time. Okay. So where does Hawking comes in, right? Notice that, yeah, I'm supposed to be talking about the contributions of Stephen Hawking, and I haven't yet mentioned him once. Okay, so now he comes in the story, right? And he started working on physics around late 60s, early 70s, all the way up to today. And actually 2 days ago, right, in arXiv, his last paper is still being edited by his second author. So he's still contributing on science all the way up to his death. But the one contribution I want to talk about is this Hawking radiation. Okay, so what is Hawking radiation about, and what does it have to do with what does it have to do with T? Okay, So I'm gonna talk about this. So Hawking, he worked on understanding how black holes behave, right? Since Schwarzschild, since Roy Kerr, Reisner, and Nordstrom, there's all these many physicists still working hard to understand the behavior of black holes. Okay? So Hawking's one of the big contributions by Hawking was the 4 laws of black hole mechanics. Okay? So I guess the students among you guys, if you are in secondary school or something, you might have learned about Newton's 3 laws of mechanics, right? That is laws of physics that is for how objects move around. So black holes also have 4 laws, and that was done by Bardeen, Brandon Carter, and Hawking. So it is this big seminal paper over here. So what are the laws of black hole mechanics? Again, ignore the equations, right? It is for decoration. It's just to, you can sort of treat it symbolically because it's going to come in relevant later. But there's 4 laws. So the 4 laws describe how the black holes behave. For example, the 0th law tells us about the surface gravity of the black hole. So near the horizon, right, gravity is very strong. But of course, we still need a number to describe how strong the gravity is. And that number is what we call the surface gravity. Right? Some black holes are stronger, some black holes not so strong. Okay? So, and then the first law is to tell us how the mass change in relation to other quantities. Okay? So it's some equation, right? But physicists are able to use the equation. If I throw stuff into the black hole, well, nothing can escape the black hole. So black hole is collecting everything. It's collecting mass. So if it's collecting mass, it will grow larger, right? And that brings us to the second law. Because this is very simple, right? Everyone can understand. Because nothing can escape the black hole, it can accumulate stuff more and more. Nothing can come out. So it can only grow fatter and fatter, right? So it keep on collecting and collecting, it keep on growing larger and larger. So in other words, black hole doesn't decrease in size. That is the second law of black hole mechanics. And then the third law is some technicalities. You cannot reduce the surface gravity to 0. Okay, but just notice this, right? Black hole can never decrease in size. Okay, so that is the one thing we can focus on. Okay, so when Hawking and his co-authors published the paper, right, they got these 4 laws, right, and they are very excited and happy. And then they notice that's weird. It looks a bit familiar. These 4 laws and these 4 equations, right? Where have you seen this before? Other places in physics. Okay, so if anyone in physics have learned other topics in physics, right, they might learn something with 4 laws also. And then they look similar. So it turns out that it is very similar to thermodynamics. Thermodynamics also have 4 laws. So for those who are not familiar with thermodynamics, right, thermodynamics is a study of how systems exchange energy. Okay, so engine, aircon, refrigerator, all those are thermodynamics. Okay, so for example, this room has aircon, right? And Singapore, today's weather is quite hot. So what does the aircon do is, we take energy, heat from inside this room and expel it outside into the environment. Okay, so that's what the aircon does. Okay, so that is thermodynamics, and thermodynamics is governed by 4 laws as well. So for thermodynamics, right, the 0th law is about the temperature. It is constant at equilibrium. And the first law is telling us how the energy change in relation to the pressure and volume. And the second law, there's something that never decreases also. It is entropy. Okay, so what is entropy? So you see that this is a long story, but it's very simple. Entropy is a number. Okay, it's a number that tells us whether certain process is possible or not. Okay, so for example, right, if I have a cup of hot water and I put it in this cold room, what's going to happen? The water will become cold, right? So why? Because entropy will increase. So if I ask you a question before doing the experiment, if I just take a normal temperature water, can it spontaneously become hot by itself? Doesn't happen, right? Why? Well, in mathematical terms, this process requires a reduction in entropy. Okay? So even before you do it, you know it's impossible. Alright, physicists know it's impossible because it violates the second law. So any process that must be possible must have increase in entropy. Okay, so all this is very weird, right? Like two different sets of laws, they are very similar to each other. So even if you don't understand the equation, I said, yeah, don't worry, they are decoration, but visually, right, they look the same, right? This thing looks a bit like that thing, you know, this equation a bit like that equation. A lot of like similarities for two totally different things. Okay, so what's going on here, right? So yeah, so why is black hole behaving very similar to thermodynamic system, where thermodynamic system is nothing to do with gravity, right? Aircon, hot water, cold water, ice, that kind of thing, right? So that is where T comes in. Okay, yeah. So that is the contribution of Wittgenstein. So we move away from Hawking for 1 minute and talk about Wittgenstein. Okay, so Wittgenstein is a PhD student of another famous physicist, John Wheeler. John Wheeler is one of the developers of cosmology and Big Bang theory and gravity also. So he asked his PhD student, because you know PhD supervisor must give some projects for students to do. So he asked Wittgenstein, what would happen if you drop your cup of tea into a black hole, okay? Or you pour a cup of tea into a black hole, right? So this is a picture of Wittgenstein pouring a cup of pouring tea into a black hole like teh tarik, right? So you pour tea into a black hole, but you see the problem here, right? Because it's a black hole, so it doesn't come up. Okay. So, but what happens if a cup of tea falls into the black hole? Okay, that is an attempt to answer the question, right? Because on one hand we have black hole mechanics, 4 laws, gravity, strong systems, and on the other hand, I talk about how hot water cools down in an aircon room. So in order to understand what's going on, we need to study the two of them together, right? So we pour a cup of tea into a black hole. Okay. Well, again, we don't have to go through the math, but the conclusion is pretty straightforward, right? So we consider what happens before and what happens after. So before is the initial state, right? Just some official thing is, what do you have before? You have a cup of tea and a black hole. So a cup of tea has temperature. It is a thermodynamic system, so it has a number that we call entropy. If I pour it into the black hole, well, everything gets lost into the black hole, right? And just now I said black hole accumulates mass, so it becomes larger and larger. So after that, what do you get? A slightly larger black hole with no more tea. Okay? So what happens to the entropy, right? So initially you have this entropy, and now you have a slightly larger black hole. Larger black hole means the size is a bit bigger, the area is a bit more. So the only thing that the conclusion that you come with is the entropy of the tea is being turned into the area of the black hole. And that is where he found the connection. The area of the black hole encodes entropy of the system. That is why both of them can only increase. They cannot decrease. That is why both of them have the same second law. Okay? So that is his great idea, that this is the first connection of thermodynamics with gravity. So the area of the black hole is encoded into the entropy of the system. Okay. So yeah. But then that brings a lot of issues, right? It raises a lot of questions. Okay, fine, you say black hole area is connected to the entropy. But if you look at the other 4 laws of mechanics, right? Entropy, the second law, we made a connection already. What is the other equations? Do you remember? It is the surface gravity and the temperature. They behave the same way. So the obvious thing that you want to say is, okay, then the temperature should be connected to the surface gravity of the black hole. Okay? But then there's a problem, right? Because anything with temperature must emit radiation. But then nothing is supposed to come out of the black hole. So what's going on here, right? Can black holes radiate? And that is the question that Hawking tried to answer. And it turns out, it can, because let's think about this a little bit, right? What is radiation and why does it have to do with temperature? Okay, so to answer the question, let us really understand a bit more about temperature. So anything with temperature emits radiation. Okay, so these are the examples, right? A human body, has a body heat temperature of 37 Celsius. And if you look at the human body through infrared camera, we actually emit radiation. Okay, a bonfire, a burning flame is glowing, right? So it emits radiation. The sun is also having a very high temperature, 6,000 degrees Celsius, and is shining brightly, right? So anything with the temperature has something to do with radiation. Okay, so black holes. If black holes must have temperature, then it has to emit radiation. So the next thing to do is, if you want to say this, then you need to prove that black holes are able to emit radiation. Okay, so according to gravity, nothing can come out. But gravity is not the only theory in physics, right? There are other theories in physics. We mentioned thermodynamics. What else? There is something that we call quantum mechanics. So if we include quantum mechanics into the theory of gravity, then it turns out that yes, actually it can emit radiation. So this is this paper that Hawking wrote, and what we now call today as Hawking radiation. Okay. Now, how does the black hole emit radiation, right? So how does it work? Because nothing is supposed to come out of the black hole. The key is through the concept of virtual particles. Okay, so this is another episode of the story, of this long story. I need to introduce more characters. Okay, I'm going to introduce to you the idea of virtual particles. So according to quantum mechanics, okay, sometimes particles can pop out of nowhere, and we don't notice them because just as quickly as they appear, they disappear. Okay, so that is the virtual particles. Okay, and it's probably happening right now. Right, they pop up and then they disappear again. We just don't notice them because the process happens really fast and we don't notice them. Okay, so you can ask, how do you know it's true? Well, people have done experiments to actually detect these particles. Right, we call them Casimir effect, and it has been detected. But normally, under normal conditions, it is too fast for us to notice. Okay, so usually two particles, these are just names, basically two, as long as there's two particles. Antiparticle and particle, they appear out of nowhere and then they vanish again. Okay, so just as a rough idea, antiparticle is something that is having negative energy, and particle is something having positive energy. Right? So for those of you who are familiar with these concepts of energy, but otherwise it's not important in our story, right? I just want to say it pop out of nowhere and then it vanish again. Okay, so that is what happens normally. But what happens near the horizon? Okay, if this pair of particles pop out too close to the event horizon, right? Then one of them could fall inside, right? One of them could fall inside, and the other can escape. So so one fall inside, the other escape. So what does it appear to someone that is a bit further away from the black hole? Right? So if you're further away from the black hole, you're just effectively seeing one random particle escaping out of the horizon. So that is what is the cause of Hawking radiation. You can say it is an illusion, right? It is an illusion because the two particles started from outside the horizon, one escaped, one fall inside, so you see one of them. So it is as if the radiation is coming out. Okay, so that is the idea of Hawking radiation. Okay, so now the job is completed. Okay, Bekenstein sort of roughly say entropy is like the area, and then people wanted to say surface gravity is like temperature. Hawking gave you an exact equation, right? A complete equation. So again, don't have an equation, but just to show you, it's there, right? So the temperature of the black hole is related to the surface gravity, and the entropy of the black hole is related to its area. So this is also one of the rare cases, right? That equations from different branches of physics appear all at the same time, because this is from what students in secondary school learn in thermodynamics. The surface gravity is students learn in mechanics, and then Planck's constant is what you learn later in quantum mechanics. So all three of them appear all at once in the same equation. That is something that's really rare, right? And it's something that physicists always try to do because, of course, the universe is one thing. We have different theories to describe different parts of it. So it is really good to have one description that it can describe everything all at once. Okay. So yeah, so that is the idea of Hawking radiation. Okay, so I'm within time. So just a few things left over, right? So now Hawking left us with this theory of radiation, but the story is still far from over. Right? So we are a Taiwanese drama. It just goes on, right? And there's still a lot of questions that haven't been solved yet. For example, this is the term for this problem is what we call the information paradox. So the idea is, well, in quantum mechanics, because we are using quantum mechanics now, quantum mechanics, the important thing here is information, right? Just like energy, information doesn't just disappear. Okay? It has to go somewhere. So what happens to the information of the cup of tea that went into the black hole? Okay? If fallen into the black hole, it's lost forever. That can't be right. Information cannot just be lost. So what happens there? Okay? So one of Hawking's last papers before he died is in this, working on this problem. And then, and because, right, in the previous slide I showed you the equation where variables from parameters from different branches of theory appear all at once. So that gives us some hope that maybe we can have a quantum theory of gravity. So that is something that physicists has been chasing for years and years and still working on it. Right? Some of you may have heard of string theory. Some of you may have heard of loop quantum gravity. All these different theories somehow has something to do with the concept of black holes, but we still don't know what yet. Okay? And then another question, a bit more off the mainstream is, well, is general relativity ultimately correct or not? Because although Einstein's theory is successful in predicting the bending of light, it's not able to explain all the phenomena. For example, the dark matter problem. So astronomers have observed the rotation of galaxies. This doesn't seem to obey the theory of gravity or Newton. So something's going wrong there, right? So if we have to change to a new theory of gravity, then we may have to rework everything that we know about Hawking radiation. Okay, so that is another problem, right? Extra things to do. Okay, so these are the problems that, yeah, they're still remaining open. So hopefully someone out there can help us to solve this problem, right? Maybe someone here. Okay, so yeah, that's all for me. Thanks, and I should also acknowledge Dr. Cindy Ng for setting this up and helping me prepare the slides. Thanks.
Yeah, thank you, Dr. Lim, for very interesting talks about black holes. I read that like Stephen Hawking was arguing with Wittgenstein that his prediction was wrong, but in the end, it turns out Stephen Hawking was wrong, but he worked out the Hawking radiation himself.
Yes.
Yeah. So I read a lot of interesting that Stephen Hawking always argue with many physicists their ideas are wrong, and then in the end, yeah, to prove them right, then he discovered a lot of things. So that's I think inspired people that you persist on the question you ask, or you want to prove things that whether you are right or not. So now we are open to questions. Do you have any questions to ask?
Hi, could you tell us more about how Hawking's radiation causes black holes to lose mass and evaporate?
Yeah, I sort of glossed over that idea. Remember just now I mentioned the virtual particles, right? One of them has negative energy, one of them has positive energy. So in Einstein's theory of relativity, energy can be converted into mass. So negative energy means negative mass. So if you throw in a negative mass into a black hole, you're sort of effectively reducing the mass of the black hole.
So only the negative energy falls into the black hole.
Yeah.
Never the other way around.
Yeah. So it is a peculiarity of quantum mechanics. Like the virtual particle pair, we sort of Well, it's quantum mechanics, right? Quantum mechanics haven't decided who is the antiparticle and the real particle yet until it happens. Okay? So one of them becomes real.
The one that flies away becomes real.
Becomes a real particle, yeah. Because a real particle, the antiparticle cannot, the virtual one cannot exist for long.
So virtual one falls into the black hole and reduces the mass of the black hole.
Yeah. Which kind of raises another problem, right? Do you notice?
Doesn't it decrease the area of the black hole?
Yes, that's the thing, right? So then the answer is because now we know, now we accept that entropy and area are the same thing. Okay? So the emitted radiation also carries entropy. And this is something we learn as students of physics. The entropy of one part of the system can decrease as long as the total entropy of everything overall increases.
So you're not
Right.
talking about the black hole itself, but all the radiation that has escaped from it.
Yes, so now that we have established both, right? So now the system is black hole plus radiation. So both entropy is still increasing.
But the actual area actually decreases. No?
Yeah.
The area keeps on decreasing. What do you expect?
So one possibility is it will keep on shrinking and shrink to nothing. So this is what we call the black hole will evaporate. And that is what we hope to detect because small black holes will shrink faster. Hawking calculated the rate of radiation. So large black hole, the radiation is there, but it's too slow, right? Until it becomes smaller and smaller, it becomes faster and faster. So that was initially what people tried to detect at CERN. So they want to detect micro black holes. And then maybe you heard in the news, right? Someone tried to push a lawsuit to prevent CERN from operating because it will create a black hole and destroy the Earth, right? It can't because black hole of that size will evaporate immediately. So that should, yeah.
This radiation that escaped from a black hole, is it all this gamma radiation or it has different frequencies or what?
Yes, it expect to have the
whole spectrum.
the black body spectrum. Are you familiar with that?
Okay.
Yeah, so because the black hole is now a thermal system, so you can have the thermal spectrum.
It looks like a black body.
Yes, yeah. Yeah, so for those who are not familiar with the black body spectrum, right? You notice that, we know this when we're cooking, right? The hot fire looks blue, cold fire, not so hot, less hot is a bit reddish, right? So if you change the temperature, you can change the color of the flame. So that is the black body spectrum. The partial explanation of it.
So how do you think that we can image the black holes if it's there's an effort on trying to get the first image?
Yeah, so currently there's a network of telescopes that they are trying to image the Sagittarius A star, right? So hopefully the image will come soon. And basically they're just collecting the light from over an extended period of time over a large angular separation. So basically just, yeah, it's as simple as a direct image. Because the black hole is very far away and there's a lot of noise and dust, so that's why the process is very difficult.
Is there any theories on what happens to the objects that get into the black hole? Is there any?
As far as we understand, right, once you fall into the black hole, at the center of black hole is what we call singularity. We talked about this just now. So because what happened to all the mass that is squeezed inside? So just now I was saying, right, squeezed into the smaller than event horizon, okay, nothing can escape, but what happened to the stuff that's squeezed in? Because gravity is an attractive force, everything collapses and all squeezed into a point. So at the center, there is a point of infinite density. So, and because infinite density, the time and space all becomes deformed in impossible ways. So if we fall into the black hole, we will fall towards the singularity, and what happens after that, we don't know. Because time and space become impossible and it's not captured in our calculations, so we are not sure.
You mentioned a photon sphere.
Yeah.
Is there any practical use of it?
Well, not practical use, but it is like a mathematical quantity that is interesting because it is a rare case where you can capture light that can orbit around the black hole, but it's not lost forever, you know. It's still outside the event horizon. So the light is having a unstable orbit around the black hole. Practical use, well, not that I can think of, like in actual astronomical application, but maybe knowing the radius of the photon sphere can help us calculate the mass of the black hole if we were able to directly observe it. That is one thing off the top of my head.
But you haven't been able to observe it.
Yeah, not yet. So
Because the light doesn't escape, right? So you can't see it actually.
it doesn't escape, but we can see around it, right? So we can see around it, and then we can sort of estimate the area, and based on other calculation, so we can sort of estimate the photon sphere, and it doesn't escape, but it is an unstable orbit. So we have many photons of light.
Some do escape, lah.
Yeah, some will escape.
Otherwise you can't see it.
Yeah.
Just now you mentioned that it is the antiparticle that get attracted into the spectrum, right?
Yeah.
And the normal matter was the photon attracted.
Yeah.
Well, how about it's the other way around?
So that was the answer. I mentioned like very quickly just now is because of quantum mechanics. Are you familiar with the uncertainty principle? So quantum mechanics is like it's gonna get weird, but quantum mechanics, right? Nothing is real until you observe it. So that is, I'm sort of like twisting words around here, right? The physicists will sort of say, but that's the idea is that. So because of this uncertainty principle, right? It is not really decided who will be the particle and who will be the antiparticle before one of them, something happens to one of them. So when it falls inside, okay, then the escape one, because it's escape, right? It has to exist in real space and time. So that has to be the real particle.
So the other one is the
Yeah.
negative anti.
Yes.
So does this already explain that why our universe we only observe the normal matter and not the
Well, yeah, partly also. The real reason is because particle and antiparticle, when they contact with each other, right, they will annihilate, which means that they will disappear and turn into pure energy. Okay, so the reason why particle and antiparticle cannot coexist in the universe, because eventually they will touch something and they get destroyed. So the remaining is what's left. So we are the ones that are remaining, the real particles.
Do you need energy to form the particle-antiparticle pair? They just come out.
Yes. Yeah, out of nowhere.
But if
It violates the conservation energy. Right?
but if they recombine, you have energy coming out of it, right? So you get energy from nothing.
Yes, energy from nothing. And also because of quantum mechanics, because there's an uncertainty principle. So uncertainty principle means the quantity of energy is not really definite if the time period is short enough. Okay, so we observe conservation energy in every day because to the rest of the universe, humans are quite slow, right? A few seconds and things like that. So according to quantum mechanics, if we are within a few micro milliseconds, right, the conservation energy can be temporarily violated. So it's violated to produce particles out of nowhere, as long as they destroy each other within the certain time.
Yeah, but when they destroy other, they produce energy,
No.
right?
No,
It doesn't.
because it starts from zero energy to some non-zero energy, and then they destroy back within the uncertainty principle back to zero energy.
Oh, it does not like normal antimatter and matter when they combine. It
Yeah.
produce-
Yeah, that's a different thing.
That's a different thing.
Yeah. Yeah, you have a question?
How do we have to make a black hole smaller faster?
Huh? How do you make a?
A
We just wait. So it's true. We just wait because Hawking radiation, right? When it radiates, it becomes smaller. And Hawking's calculation says that the smaller the black hole, the stronger the radiation. So if you wait a bit longer, it becomes smaller, it emits radiation even stronger and faster. Then it becomes faster and faster, so we don't have to do anything. We just let the black hole by itself, it will just radiate and disappear very fast.
But your very fast means billions of years lah.
If you start with a large black hole in the first place, yeah. But if you start the LHC black holes, right, like a few grams mass, that will disappear very fast. It will shrink very fast. So yeah, it's like to the power of T/1/4. So yeah, very fast. Yeah.
So like you mentioned like the virtual pair, right?
Yeah.
So if you can observe the radiation, then it's like because are the pairs like entangled? So like if you can see the radiation, then won't you be able to know what's happening?
No, we don't. We don't. So your idea is entangled. For entangled pair, right? One falls into a black hole. There is a loophole in quantum mechanics. For entangled pair, right? How do they know they are entangled in the first place? And the key point is, both sides need to make some observation, and we wouldn't know they're entangled until later we compare the data. So if one pair falls into a black hole, right, and you can't come out, so you don't know what's happened inside, it's lost already. So we won't know what's happened inside. Yeah, so quantum mechanics loophole. Yes?
You were mentioning just now that you are bending space and time, correct?
Yeah.
So is there any possibility that in the future man can just travel through time?
Yeah, interstellar, right? So it is...
Because I remember, I mean I took one module of quantum physics many years ago, and of course one of my professors saying, that was probably 30 years back. So one of my professors during that time was telling us students that there's a possibility that we could travel in time in the future.
It is possible, with some caveats. So, so the idea is, okay, in order to travel long distances, right, you need to bend space and time in a specific way. Because you bend wrong way, you actually have to travel further. You make things worse, right? So the story is actually very interesting. It's actually the concept of wormholes, okay? And the first wormhole considered in relativity, right, was actually a professor trying to set an exam question for his students. Okay? So then he sort of, it's an exam question. And it turns out that in order to have to bend in the right way, you need to have energy that sort of violates another law of physics. So that might be a problem. So in order to bend, to become a shortcut rather than a long cut, right? You need some mass to bend, right? So we consider what type of mass to bend it in the right way, and it turns out that this mass could violate another principle of gravity, so which is called the null energy condition, in case you want to look it up. But then again,
so it's not possible presently.
Never say never, because again, then at the same time, people are still developing quantum mechanics. So quantum mechanics, like a lot of weird things can happen, including violating the null energy condition. Okay, but quantum mechanics, right, it has to be small amounts. So we can imagine, if our technology is sufficiently advanced or some advanced civilization to able to produce large amounts of these substances, then maybe yes. Yeah.
Speaking of alien technologies, if you have technology to manufacture black holes by squeezing matter to a very small size, if you do something, what would you do with this black hole that we manufacture?
I don't know, play with it. Big lenses. Possibly, well, because one thing I didn't mention is you can cause time dilation. So I can imagine, okay, whatever things that you want to need to slow down time. Some really unnecessarily advanced refrigerator you want to store food, you know, that doesn't go back very quickly, so put it near a black hole, time slows down. You can keep it for 1,000,000 years, take out, you can still eat. I don't know, just random.
Can stop aging.
No, because for the person experiencing it, it's still aging normally. That is the unfortunate thing. Yeah.
How near is the nearest
Black hole.
from us?
Don't remember. I think it's the nearest one that we know of. I think is 4,000 light years away. Is it? Like around 4,000 or 400. Yeah, I might be off by a zero. So 4,000 light years away. So what's a light year? Do you guys know? Like the light year is actually a long distance. 1 light year is the time light takes to travel for over a year. So that means the distance is so far that light takes 4,000 years to cover that distance. So the nearest one that we know of is very far away.
And is the position stagnant? Is it in the same place or is there any movement or something?
Well, there is what we call peculiar motion. It is moving, but we are sort of moving along with it with the rotation of the galaxy. So if it's moving, but if the 4,000 light year distance won't change much over a few million years. Just a small movement.
So to answer my own question, is black hole an ultimate garbage truck? We can just throw our garbage into it and
Yeah.
If you go this way, you
if we manufacture one, we just throw garbage into it. It's an ultimate dump hole.
Yeah, you can throw everything inside. Although that's the information paradox, we don't really know what happens to the information that you go inside. It could be lost forever, but since it's garbage, you don't care what happens to it. Yeah, just throw. But although you are increasing the entropy of the universe by doing so, yeah, which ties back to global warming, right? More garbage, more heating, more entropy, climate change.
So if you go with garbage in, you cause heating?
It will increase the entropy of the universe. So, now why is that a problem, right? Imagine, okay, entropy of the universe can increase. So imagine all the processes that could possibly happen have happened, and the universe have achieved a state of maximum entropy. That means nothing else can happen anymore. No more processes. So the term, if you want to look it up, is called the heat death of the universe. So if we're increasing entropy, we are sort of accelerating that process.
So better to keep your garbage to yourself.
Yeah. Yeah. Save the environment.
The general relativity, does it still there's a conclusion whether the universe is expanding, shrinking, or staying constant?
Currently, based on observation, is expanding and is accelerating. So that is also one of the big achievements of relativity, is able to describe how the universe evolved over time. So in the past, we know Big Bang Theory. In the past, the universe is very small, and it's expanding, until what we see today. And what we see today is galaxies all around us. They look as if they are moving all away from us. It's not they are actually moving away from us. It's the entire universe is expanding. So that is the expanding universe. So that is the big discovery made in 1998. Yeah. So yeah. In fact, our Dr. Ng knows some of these people. They are part of the team that discovered the acceleration of the universe.
The Big Bang Theory does not explain dark matter and dark energy.
Yes and no. Well, if you accept the cosmological constant as part of Einstein's theory, then you can sort of have this explain this behavior, right? So, but then you have to put in this extra constant, some extra variable in your equations.
But Einstein says that was his biggest mistake, isn't it?
Yeah, and it turns out to be actually is there. So, so the story is Einstein wanted a specific solution for the universe, and during that time, we didn't know the universe expanding.
He wanted a steady state.
He wanted a steady state universe. So in order to achieve that, then he needs to put in a cosmological constant. And then Hubble discovered the universe is expanding, so actually it's constant not needed. And then he think, okay, it's his biggest mistake. And then in 1998, the people discovered that the universe is accelerating, not just expanding, it's accelerating. In order to achieve that, we need to put back the cosmological constant. So Einstein's biggest mistake is not really a mistake.
But the cosmological constant would be now a negative number, right? I mean, for it to
Positive. It has to be positive.
Positive.
Yeah. So, but it's just a constant.
I thought the positive number is to restrict it to the steady state, right?
Is the equations no, because it's the technicalities of the equation. Because for a static universe, that means you need a rate of change for something to be zero. So you need this constant to make it zero. You need to cancel some terms, and then but now the story is different, right? So now we have an accelerating universe with some certain distributions of matter and things like that. So we need to put back the cosmological constant again. So
They mean by string theory.
string theory. So string theory is one attempt to have a quantum gravity. So quantum gravity is a theory that is supposed to unify gravity and quantum mechanics. Because these are two very different theories. And physicists are trying to quantize gravity. Okay, because ultimately all the theories should be quantum in one way or another. Gravity is this last theory that haven't been quantized yet. String theory is one attempt to quantize gravity. So the idea is the fundamental units of the universe, right, that make all of the atoms and molecules and space and time are little strings. So when strings vibrate in a certain way, you get a proton, for example, or you get a neutron. So if the string vibrates in another way, you get the graviton. And this graviton can be used to explain the theory of gravity. So that is string theory.
They're parallel universes? No.
Parallel universe is different. Do you mean higher dimensions? That's because that's in string theory. So string theory, in order for string theory to work, right, we need the universe to be more than 4 dimensions, right? So right now we have 4 dimensions, you know. We have up, down, left, right, forward, backward, 3, and then time, 4. Okay, but string theory doesn't work in 4 dimensions. You need 5, 6. So there's an extra dimension that we could have stepped into, but we can't yet. We can only go in 3. So, but that is very hypothetical. So the reason why we only see these 3 dimensions, right, is because all these extra dimensions are very small. Okay, so yeah, the common example is like if you look at the wire close up, right, like this this railing bar over there, it is a 3-dimensional object, right? It has size and height and width and everything. But if you shrink it to a small size, or if you look at it from very far, you just see one line, right? So you see one line, people think a line is just 1 dimension. So if things are small enough, it can appear as if the dimensions is less. So that is what string theory thinks our universe is. So the extra dimension is because it's too small.
It means the parallel universes don't exist?
Well, string theory predicts it to exist, the extra dimensions, but we haven't observed it yet. So no evidence of that yet. But then when you think of parallel universe, right, that goes to another interpretation of quantum mechanics, where, you know, uncertainty, because in quantum mechanics 2 possibilities can happen, and the only way for this to work is the universe branches out and creates this parallel universe. That is another interpretation of a parallel universe under quantum mechanics, which is outside string theory. Well, under string theory, but different regimes.
We all are just vibrating. It's all vibration.
Yeah, of the strings, right? Yes. And actually, even without string theory, everything is vibrating. Atoms and molecules, they are all vibrating. And that is how we have a body temperature and all that.
So can we actually observe Hawking's radiation experimentally?
So far, not yet. The problem is, well, the black holes in space are too far away, and because big ones have, just now I said, right, the larger ones have very little radiation. Okay, so and people at CERN, they try to observe it by making small black holes that evaporate really fast, so they are left behind as the radiation, but haven't observed yet. So far, what they did manage to do, right, is to simulate Hawking radiation. Okay, so people did this condensed matter experiments where all these substances, they mimic the behavior of black holes. And that one, apparently it has Hawking radiation there. So it's like it's not a theory of gravity, but they're described by the same equations and things like that. So in that sense, yeah, it has been observed.
They have not managed to create black holes in the NHC, right?
Not as far as I know, not yet. Although they are trying to.
There's no further questions. There's thanks.
So in the US we have Professor King. Yeah, because here, right? So, depends on what you want to do. Because for me, right, we are, my research is on this chemical, we didn't really, but we can, because activation testers actually is the observatories and all the LHCs, they will check out for astronaut, they have been like one astronauts from Asia before. They are scientists or pilots when they train in NASA. So that is much later in your career actually. So if you want to go like for example study, right, you can start with the US, bachelor degree, either continue masters here or overseas. I studied, I did everything here in NASA, but there are others who go overseas. So we are bachelors of physics. For this field, Hawking is from Cambridge, so it's the UK, Cambridge, Oxford. And then also, well, other places as well. In the US, Stanford. Those are prestigious universities. Yeah, but I would say for bachelor, right, for a starting point, you can like, go to any university first, and then there's a possibility to do a PhD. Yeah, because I don't know, because I mean I'm thinking on the back of my head, okay, Trump immigration, and in Europe, right, also they have a lot of all this immigration issue. It's very hard for Asians to find. So I would say okay, Taiwan, Japan, those are good places. With a lot of advanced research there. Japan
learning is just as good.
Yeah, just as good. If not better in some areas.
Thank you very much.
You're welcome. Oh, sure.
I also don't know how to use the Android. Use the one more.
at
the
this?
stretch.
Oh, okay, that's cool.
The first part which you said, like you told about the red sheet, we
Oh,
really
yeah,
created
yeah,
that,
okay.
on the rubber sheet. or
Ah,
something.
okay, that's great. Oh,
So we just started to this session,
ah,
getting to fold it.
Yeah, it's a pretty much the first session, but thanks for coming down because it really cleared my
oh,
John, right?
Kim Yong.
Yeah, he does.
Kim Yong. Yeah, yeah, yeah.
At time, I haven't come to science for a day where they come and give us students coming.
No, I'm not familiar with this. Oh.
So you know that
No, that was you. So, but yeah,
What is your research?
on this one, yeah, black holes and specifically